Have you ever wondered how your data travels safely over the internet? It's a journey fraught with potential pitfalls, a digital odyssey that takes your data from your device to the far reaches of the globe. This data, whether it's a heartfelt message to a friend, a crucial business document, or a funny cat video, is broken into tiny packets, each sent hurtling through a vast network of routers, cables, and servers. It's a process that's not always smooth. Your data can encounter various forms of interference or disruption, causing errors that can corrupt it, making it unreadable or even worse, inaccurate. But fear not, there are measures in place to protect your data from these digital gremlins. To understand these measures, we need to delve into the intricate world of error control. But how does the system ensure that your data reaches its destination accurately? Let's delve into the world of error control. Errors in data transmission can occur due to various reasons. They are the unwanted guests that sneak in through the back door, disrupting the smooth flow of data. Let's delve into what causes these nuisances. Noise and interference, much like an unwelcome radio station playing in the background, can corrupt your precious data. These external signals, electromagnetic interference or crosstalk, disrupt the harmony of data transmission. Then we have transmission failures. Imagine you're sending a letter, but it never reaches its destination. That's what packet loss is like. It could be due to hardware faults, congestion, or other network issues. Hardware problems, such as faulty network cards, cables, or switches, can also cause data corruption. It's like trying to listen to a song with broken headphones. Lastly, software errors. Bugs or misconfigurations can lead to incorrect data processing or transmission. It's like a chef misreading a recipe and adding salt instead of sugar. Given the numerous sources of potential errors, error control becomes an essential aspect of data transmission. Let's understand the types of errors that can occur during data transmission. Firstly, we have single-bit errors. As the name suggests, these errors affect only one bit in a data packet. It's like a single letter in a word getting flipped, altering the meaning of the word. On the other hand, we have burst errors. These are a bit more severe as they affect a sequence of consecutive bits. Imagine a whole sentence where multiple letters are misplaced or altered. These burst errors are typically caused by significant noise or transmission issues. So we have single-bit errors that are like single typos, and burst errors that are more like a series of typos in a sentence. Both can create havoc in data transmission by altering the intended information. Now that we know the types of errors, let's explore how these errors are controlled. Error detection is the first line of defense in error control. To ensure the integrity and reliability of data, various methods have been developed to detect errors during data transmission. Let's dive into some of these methods, shall we? Firstly, we have the parity check. This is a simple yet effective form of error detection. Here, an extra parity bit is added to the data so that the total number of ones in the data is either even or odd. This is known as even parity and odd parity, respectively. If the parity doesn't match, we know there's been an error. Though it's an effective method for detecting single-bit errors, it falls short when it comes to burst errors. Next on our list is checksums. A checksum is a calculated value derived from the data to be transmitted. The receiver recalculates the checksum upon receiving the data and compares it to the received checksum. If the two don't match, an error is flagged. This method is more robust than the parity check and can detect both single-bit and some burst errors. Finally, we have the cyclic redundancy check, or CRC. This is a more sophisticated method that uses polynomial division to generate a checksum. The strength of CRC lies in its ability to detect burst errors, making it a robust tool in our error detection arsenal. It's important to note that while these methods are effective at detecting errors, they don't correct them. They merely flag that an error has occurred, but detecting an error is half the battle. Once an error is detected, it can be handled appropriately, either through error correction or retransmission. These error detection methods are the guardians of data integrity. They stand on the front lines, ensuring that the data we send and receive is accurate and reliable. But they are just one part of a larger error control system. While error detection is crucial, it's not enough. This brings us to error correction. Error correction techniques not only detect errors but also correct them. Imagine that you're trying to have a conversation in a noisy room. You might mishear something, but based on the rest of the conversation, you can probably figure out what was said. That's a bit like how error correction works in computer networks. Instead of asking to repeat the entire conversation, you fill in the blanks. Now let's dive into some of the most common error correction techniques. First up, we have forward error correction, or FEC. Here, redundancy is added to the data before it's transmitted. This gives the receiver the ability to correct errors without needing to ask for the data to be sent again. It's particularly useful in situations where retransmissions are costly or impractical, like in satellite communications. Next, we have the Hamming code. This is a type of FEC that can detect and correct single-bit errors. It can also detect but not correct double-bit errors. Think of it like a superhero with a very specific set of powers. It can't fix everything, but when it comes to single-bit errors, it's got you covered. Finally, there's the Reed-Solomon code. This is a particularly powerful error correction method, capable of handling burst errors. If you've ever scanned a QR code, listened to a CD, or watched a DVD, you've benefited from Reed-Solomon code. It's a bit like the Swiss Army knife of error correction, versatile and reliable. But as with any system, it's not perfect. Sometimes, despite these error correction techniques, a message gets so scrambled that it just can't be fixed. It's like trying to piece together a puzzle when half the pieces are missing. In these cases, the system might need to retransmit the data. This is a bit like asking someone to repeat themselves when you didn't catch what they said. It's not the most efficient method, but sometimes it's necessary. In some cases, despite error correction techniques, retransmission might be necessary. Retransmission strategies ensure reliable data transfer when errors are detected. That's the goal, but how do these strategies actually work? Let's start with automatic repeat request, or ARQ. This is a popular retransmission method that hinges on the power of acknowledgement. Imagine sending a letter through the post. You'd want to know it arrived safely, right? In the digital world, the receiver sends an acknowledgement, or ACK, for each packet it receives successfully. If the sender doesn't get an ACK within a specified time, it assumes something's gone wrong and retransmits the packet. It's like getting a text message saying your letter arrived. No news is bad news. But what if you're sending a book, not a letter? You wouldn't want to start sending from page 1 again if the only thing lost was the last chapter. That's where Go Back and ARQ comes in. This method allows the sender to transmit multiple packets at once, a bit like sending several chapters of the book in one go. However, if an error is detected, the retransmission starts from the point of the error, not the beginning. It's a bit like realizing you missed out a chapter and going back to include it. Now, imagine you're sending a whole library of books. You wouldn't want to resend everything if just one book got lost. That's where selective repeat ARQ shines. It's more efficient than Go Back N because it only requires the retransmission of erroneous packets. Think of it as just sending the missing book instead of the whole library again. These retransmission strategies are the unsung heroes of data transmission. They work behind the scenes, making sure our data arrives intact, even when the digital universe throws its worst at them. They're the postmen and women of the digital world, braving the storm to ensure our data gets to where it needs to be. So, through a combination of error detection, correction, and retransmission strategies, our data is kept safe during its journey. The impact of these error control mechanisms is far-reaching. Imagine a world where reliable data transmission wasn't a given. Every email, every photo sent, every online transaction would be fraught with uncertainty. But thanks to error control, we can trust in the integrity of our data. In the realm of telecommunications and broadcasting, error control is the unsung hero. It ensures that your favorite show streams without a glitch, that your phone calls are clear and uninterrupted. In wireless communication, where signals are susceptible to interference and noise, error control is an absolute necessity. It ensures that your messages, photos, and videos reach their destination intact. And when it comes to storage and data transfer, error control safeguards your precious data, protecting it from corruption and loss. Through error control, we ensure that our data travels safely and accurately, regardless of the challenges it may encounter along its journey.